I'm Matt LaPlante. For those of you who don't know me, I'm the technical director for the Tessent products in the Americas, which really means I manage the AE resources that I'm hoping all of you are working with and having success with. So I've been at Siemens EDA for 20 years, but that also, of course, includes Mentor Graphics. And for those of you who have been doing DFT for over 15 years, you may also remember Logic Vision. Prior to that, I was an ASIC designer for LSI Logic. But today we have, I think, some really great presentations for you, spanning from some methodology, best practices, and some results from some of our newest features. So our first presenter today is going to be Jay Jahangiri. Jay is the DFT Product Management Director for Tessent Products at Siemens EDA. He spent 29 years in DFT and has experience from Texas Instruments and Raytheon prior to joining Siemens. He is also the co-inventor of 2 US patents and has written several articles and papers. So today's talk is going to be on shift-left DFT techniques, including RTL complexity analysis, RTL test points, and flow optimizations with quick synthesis. So please welcome Jay Jahangiri.
Thank you, Matt. For those of you who might be a little bit surprised of the title of the presentation and what's on the agenda, we did have some of the customers that were going to be presenting today that had to cancel and back out. But I'm pretty much going to be covering a similar topic than what they were going to be talking about. So I'm hoping to be able to give you a good flavor of the capabilities that are in the tool that they were going to be talking about, but with a little bit of twist, and I'll give you some visibility into some of the reports and some of the other functionality that maybe wasn't going to be talked about. So I'm Jay. Jeff Mayer is also on the title because he helped with preparing a lot of this presentation. He's the product manager on the team that works on this capability. Okay, so what I'm going to talk about today is just a few different things. So I'll start kind of high-level view of the shift-left methodology, and then talk about some of the capabilities that are available to you today. And some of these are pretty new, actually. So I'll talk about just high-level syntax handling, the complexity analysis, the RTL complexity analysis, and suitability for test point insertion that's in the tool. And then go into DFT analysis and insertion at RTL, show you some comparison results and comparing essentially test points at gate level versus RTL and how those results are different. And then I'll wrap up with just a couple of slides on quick synthesis. So just a little bit of a history. So as you know, for a long time, we've traditionally way back when you were designing chips and you were doing DFT, we did insertion of a lot of the DFT hardware like memory BIST, logic BIST, compression, and things like that at gate level. So you'd have your synthesis, go through and do RTL DRCs for DFT, insert the hardware, and then do another synthesis. And that has, over the years, has evolved to the point where we do the majority of the RTL insertion, of the DFT IP insertion at RTL. So today, EDT, logic BIST, SSN, everything is inserted at RTL, so then we can do all of the majority of the DFT DRCs, majority of the DFT verification is done before that, that synthesis step. And that really helps optimize a lot of things. You can catch a lot of things early and make sure everything is working before you go through synthesis. A few things we're still, we're done at gate level, including test point insertion and analysis, expounding, and for scan insertion. So now we've kind of shifted those last 3 pieces, other than scan insertion, back to RTL. So test point analysis and insertion, expounding, and wrapper analysis can now be done at RTL. So you essentially have even more of the tasks that you would have to do early for the design much more earlier. And that obviously helps productivity, and you're less likely to be in the critical path of the chip getting out. So today we're going to kind of focus on these last 3 pieces and how those are being done now. Of course, scan insertion is still at gate level. So just a couple of high-level notes. So the way the analysis is actually done in the tool. So the tool has a capability inside that can do a quick synthesis. So when we read RTL, we can do a quick synthesis and do a lot of the analysis is actually done on that gate level design. And I'll talk a little bit later about how you also have access to that quick synthesis functionality in the tool. And you can use that same capability to speed up your analysis much earlier and do a bunch of other stuff, including things like ATPG, while you're still at the earliest stages of RTL design. So the way the tool is actually working is we take that gate level design and then the analysis is done and it gives the tool a lot of the visibility into all the different nodes that exist in the design so that the results they're available much earlier, and you can look at it. You can see what where the test points are, where the tool can or cannot insert test points, and I'll show you some of the reports that we have for that. And just one note here, you can see it says that the synthesis is done on whatever RTL you have. The insertion is done on Verilog or System Verilog. Just a couple of examples of how the tool does RTL editing. And this is similar to how we do RTL editing for different capabilities, but when we talk specifically about test points, that's one of the key 3 topics we'll talk about today. So you can see the RTL on the right is the modified version where the tool is actually doing direct structural editing to insert a control point. As you can see, the original RTL is pretty much maintains the same look and feel. And that's important to a lot of people because obviously you don't want to get something back out of the tool that looks like a machine generated bunch of code and you don't know where it started from and you don't see exactly where the changes are. So the changes are very precise and can be done as a direct editing like that, or the tool can also do functional calls when it needs to edit things like on expression boundaries. So it can actually create a function, it can edit the RTL with minimal changes and effectively insert those test points where they need to be. So that's kind of one of the principles that we have always had when we do these kinds of RTL editing to make sure that we maintain the look and feel and make it as simple for you. So as part of that, part of the analysis the tool does, we now also do RTL complexity analysis and the suitability analysis. So what this functionality is that the tool will look at your design, and before even you have to kind of go through all the other steps, it can give you a very nice detailed report so that you can see, well, first of all, at a high level, is my design a suitable design for RTL test points? How complex is it? And where are the complexities in the design? And then based on that, you can get a report of specifically where the areas are in the design that you want to maybe go and see if you can improve, right? The tool can't change your design, right? Functionality has to remain the same. But if parts of the design are part of the RTL are very complex, where you can't insert test points in it, for example, the tool can't do it, you'll want to know where those places are. And that's what this report will tell you, both as a summary and as a detailed report. Today, I'm just going to show you some screenshots of what that summary looks like, but you can also get a much more detailed report so it becomes actionable, so that then you can decide where do I go and make these changes. So the command that you would use is report RTL complexity. And this is available in the test-points-RTL context. So if you're familiar with the tools, you set the context when you first come in. And now you have this new capability. And the options that I'll talk about are the first ones, which is a dash summary with the 2 different levels of effort. The summary gives you a really nice report that kind of looks like this. Now, at the top, the first 2 lines, kind of a very high-level summary. How complex is your design, and how suitable is it for RTL insertion? So after the analysis is done, you have a very nice, clean summary of how good is my design for this, then all the details about it. what the tool learned about the design. So you can see it has the overall design profile, exactly how the total number of gates in the design, where those things are located, which ones are editable or not. I'm going to need my glasses for this part. There we go. And exactly where are the gate pins, which ones are visible, which ones are editable, and you can get a summary of the number of them, and then you can get a detailed report later. And then at the end, it also gives you a summary of the RTL test points that it actually was able to generate and insert. So if we kind of dig into that report a little bit more, on the left is the report before doing the quick synthesis. As I mentioned earlier, the tool is going to do quick synthesis in order to be able to do this analysis. So there's not as much information available before we go through that quick synthesis, but after quick synthesis, you get much more details about exactly where those sequential cells are, which ones are floating or are not, where they're constants, where the tool can't make changes. And then at the bottom, you see it has more details about which parts of the design, which nodes are editable, which ones are possibly editable, and which ones are not editable. So you can, right off the bat, get an idea of how the tool is able to or not able to edit your design for RTL test points. Okay, so that's kind of the summary that you get right off the bat. Then you can also do things after test. You also get a different report after test point analysis, where at the bottom you can see it tells you exactly. If I had a pointer, I would point to it. But if you look at the very bottom, post-analysis and post-insertion, after the tool has actually inserted the test points, it will tell you how many control points and observe points were requested or added. Actually, how many were added based on the constraints that you set when you told the tool to go insert the test points. If I can see that. Yeah, and the last two lines there, you can see which test points are actually merged in RTL. And the example on the right that you see, that's showing an example of a place where the tool might have identified two different places to insert a test point, but it really needs to only control one of them. So it can actually merge those two test points, and it'll tell you exactly how many of those it was able to do. Okay. So you get more and more detail as the tool does more. So after quick synthesis, you're getting more details, and then after insertion, it's able to give you more information about it. So there's also an option to do a high-effort complexity analysis. So we do a complexity analysis based on your design, and we tell you, here's where we can insert our test points or not, but there's parts of the design that we can't touch. Now, what if you told the tool, ignore that, the parts that you can't touch, tell me what if you could touch them? How much better could you do, right? How much editable will my design be? That's what high effort does. It essentially ignores some of the constraints that we normally would have in a real case. And then it gives you an idea at the very bottom. It says, you know, how much of the test points would have been inside functional blocks or within the logic that it couldn't edit. And then you can, based on the detailed report, you can actually identify where those are. So that's where it becomes actionable. You can say, well, maybe I can change something. I can talk to the design team, or I can change something so that it becomes a better design for test, and we can actually insert test points in the right place and get better results in the long run. So this complexity analysis is a really useful tool just to give you an idea of how well your design, your RTL, is going to behave for these kinds of work. So DFT analysis. So there's multiple things that the tool can do now. As I said, there's test point insertion, there is expounding and wrapper cell analysis that the tool can do now at RTL. The good news is if you're familiar with being able to do those things at gate level, it's the same commands. So you essentially have the ability to run the same commands you're used to using at gate level, but now in the -RTL context. So the commands on the left are available now in the DFT-RTL, and the ones on the right are available in the -test points-RTL. So same commands, same functionality, so the analysis can now be done at RTL, and you can then optionally tell the tool to insert it. So how would you do that? So for wrapper analysis and expounding, really the important part is the green commands on the right. So you essentially, you read your design, you tell the tool what it is that you want to do with the context and the settings, and then you set your expounding options, how you want the tool to do it, you analyze that, and then you can write out the report, which tells you exactly which where those expounding logic would go. And then the same thing with the wrapper analysis, you would write that into a separate report. And then optionally, you can use the process DFT spec command to actually have the tool do the insertion for you. Right. So same command you're using today at gate level can now be done at RTL. And the same thing for our RTL test points. So we have the RTL test points, the dash test point dash RTL context here. And the set test point commands, you define where your add non-scan areas are, where you don't want the tool to touch, and then report RTL complexity, which I mentioned just now, just to see how your design looks, analyze test points, report them, and then process DFT spec to insert them into the design. So some results comparison. So we had on a bunch of different designs, we compared how would pattern count change compared to gate level RTL test point insertion versus RTL. You see the design statistics on the left. On the baseline, you see the test coverage and pattern count with no test points. And second group of data is the gate level results, and you can see the percent coverage, the bolded numbers, the percent reduction in pattern counts, 60%, 70%, 53%, and all the way down in different ranges. And then the last group of data is for RTL test points. So pay attention to, first of all, the RTL suitability. So that's the suitability for test point insertion that the tool determined for all these designs. Number of test points, which of course, in some cases will be different. And you can see there's one case there, 1305, that's highlighted in green. Quite a few, actually fewer number of test points needed than gate level. And the pattern count reduction is actually a lot more, 55%. But there's a range. There's some of them that are not as good, but overall, we see very good results with comparing the gate level to RTL. And what I've seen in some customers, obviously it saves a lot of time and effort if you can do most of the work at RTL. They will do that, and they might still do some gate level RTL, some gate level test points after, right? Just to see what else they can get. But this moves the majority of the work, and in some cases, all of the work from gate level to RTL, and you get similar or better results sometimes. Okay? So just a quick, I think I'm almost, yes, question? Yeah? Good question. So these tests. Okay, yes. The question was, in the previous slide, we didn't really compare test coverage. And the reason is that these test points are designed for test pattern reduction. The title of the talk, I think that I was actually looking forward to see also talks about test coverage, but these test points are designed to be test pattern reduction. So everything you see here is at the same coverage. Right. Yes. Yeah, so the question is, how is it possible that the tool can do better at RTL in some cases than gate level, right? So it really, a lot of times it depends on the complexity of the RTL. If it's something that is very editable, it actually is easier to insert test points at RTL because we can insert them exactly where we want them. And then it might also be that the gate level analysis couldn't do something because something happened during synthesis. I don't know the exact reason for these cases, but we've seen results in both ways. Okay. Yes. So the question is, when we insert test points at RTL, do we end up with more logic added? So if you look at the number of test points, right, in some cases, there are actually fewer test points needed at RTL, right? And the test points are, AND gates or gates. So the logic size of what we're adding is similar, right? It's mostly the number of test points is what's going to determine how much logic you're going to add, right? Which varies. Yes?
How did you decide how many test points you want?
So you're asking, how do we decide how many test points to insert? And different people have different parameters. So I've seen customers that will say 2% or 1%, 1.5%. I don't remember exactly what these were, but they were in the same range. So we do our experiments in the 1 to 2% range.
Like before, so sometimes I try different test points. In my case, right? Try different like 6,000, 9,000, 7,000 test points, and compare the test coverage down and find. But within the 7,000, the test coverage improvement is not much. So I decided using the 5,000.
Right. Yeah. But yeah, I think you're still thinking about test coverage, which can change, right? It does impact test coverage to some degree, but for ATPG, they're designed to be test pattern reduction test points. It's possible, depending, and I think you get a feel for it after a while. The question was, did you have to do iterations to get to the right number? Sometimes you do at first, but over time, I think once you get a feel for how the tool performs, most people kind of have an idea where they want to be, right? Okay. Quick synthesis. So I mentioned quick synthesis, which is the engine that the tool uses to initially kind of do a quick synthesis of the RTL and then do some of this analysis. What we've seen is that you can actually save a lot of time and help with being much more productive in your flow if you also take advantage of the quick synthesis that's actually built into the tool. And it's about 40 times faster than normally, if you're doing a full optimization with your synthesis tool. So real synthesis takes a long time, and quick synthesis, much faster. So what you're able to do within the tool, you have access to those commands that you can use. You can go through, read your RTL, create a quick synthesized version of it, and then go off and do things like even ATPG. And we've done comparisons to see how that compares, and I'll show you, I'll give you an idea of kind of how close we are. But for coverage debug, it's actually a really good tool because you can much earlier add RTL without having to wait for somebody that's going to have to do a very optimized synthesis for you. You can get a pretty good idea of where are the problem areas, where do you have to do some debug and get better results. And also with pattern count, you won't get as close because it's kind of different, but you still get an idea. You can do some comparison and get a relative idea of, okay, if I make some changes here, how will my design change? So the way you do it is you just read your design, you tell the tool, and I think I have the commands. Yeah, you read the design, read your libraries that might be needed. Normally, you don't need the libraries because there's a set of RTLC libraries in the tree that you have. So you already have all the cell libraries that's needed for quick synthesis. Unless you have some custom library cells that are implemented at RTL, then of course you have to read those in. You tell the tool to run quick synthesis and you get a synthesized version. And there's different options you can use to do that. So here's you can see, you read the design, libraries, set quick synthesis options. There's a couple of options in that command you can specify. When you issue the command check design rules, which is when we running DRCs, that essentially performs quick synthesis under the hood. So after you've done check design rules, now in memory, you have a synthesized version of your design, and you can just write out that using the right design command and use it now for your next step. For example, you can go and run ATPG. Or first do scan insertion, you can then do ATPG on it just to get an idea of what your coverage looks like. And really the benefit we've seen, as I mentioned, it's DFT flow development. So you can do all of your work much faster, 40 times faster to run through quick synthesis than it is to run a regular synthesis on average. And you can do, again, shift left is the whole theme of this talk, right? So how much of your work can you do much earlier? Debug, verification of what you have to do at the RTL helps tremendously. And then, yeah, so there's the more detailed commands. And the last major bullet on this, performing ATPG identify outliers. You can also use analyze compression. So analyze compression is the command in the tool that you can do experiments to see, what kind of configuration you need for EDT and what gives you the best results. You can do all of that at RTL. So just to summarize, this is really the vision or the view that we have of what's an effective DFT and shift-left strategy. You don't need just insertion. There's analysis, insertion, and verification. So being able to do things like DRCs early on, RTL complexity analysis, now with test points, wrapper cells, and X-bounding analysis, all of that, doing that all at RTL. Obviously insertion, doing it hierarchically for all the IP that we've talked about. Design editing, there's very powerful RTL design editing capabilities in the tools that you have access to in any of the tools that you're using. Handling complex Verilog, and as I mentioned, being able to preserve the look and feel of the RTL, of the original RTL. That makes things a lot easier because you know what the tool did. They talked about verifiable AI and being able to verify the results. You can see exactly what the tool did, so you can see if you're happy with the changes. And then verification, debugging the issues, including ATPG, any kind of DRCs, anything that's going to prevent you from getting really good results in your design, doing that at RTL. So this is really the full picture of what you can do with RTL shift left. So summary slide, I know I'm pretty much out of time, so I'm going to leave that up there. What I really, just to highlight with you is the new things are the complexity analysis, the analysis of RTL test points, X-bounding logic, and wrapper cells, and now all at RTL. And then quick synthesis is also a capability you have access to in the tools. So take advantage of it. It could make you productive and make things a lot easier. Okay.